Maybe it's visible more now. Just keep it some different orientation just for a better visibility. Yeah.
Yes, Priya, go ahead.
Maybe it's visible more now.
Priya, kindly go ahead.
Okay, sir. First of all, good afternoon, everyone present here, our guest of honor, authorities, and faculties. I, Engineer Priya Mittal, Assistant Professor, Department of Civil Engineering, BFCET, feels immense pleasure to host this FDP session today with you all. Now, I would like to welcome our today's second expert, Dr. Ekta Singla, Associate Professor and HUD Mechanical Engineering Department, IIT Ropar. She is recipient of National Award, Sheila Bhaya Award 2016 from Institute of Engineers. She had also received National Doctoral Fellowship AICET during her PhD from IIT Kanpur and Institute Gold Medal during her Masters in Thapar University, Patiala, which has shown consistency in her hard work and contributions. Her current research interest inclined towards the advanced direction of modular robotics and hybrid manipulators. Just before joining IIT Ropar, Dr. Ekta had experience working in two international groups in Europe in the area of rehabilitation robotics and evolutionary robotics. Recently, Dr. Ekta has initiated a move to assist in uplifting the interdisciplinary field of robotics with the institute and around. She established a collaboration called Punch Robotics among 9 faculty members of IIT Ropar and many others from nearby institute towards the establishment of common platform for robotics. On behalf of Baba Farid College of Engineering and Technology, we welcome you, ma'am, to speak over today's topic, robot kinematics. Thank you so much, ma'am, for your kind presence.
Thank you. Thank you very much, Ms. Priya. Actually, it's Engineer Priya. Okay. And others, I thank you for this opportunity. If I'm audible completely,
Yes, ma'am.
because yeah, audio needs to be checked. And thank you for the introduction and for this organization, because I always say with one line that uplifting of robotics, may it be my work or may it be punch robotics as you have just introduced, uplifting of robotics in India is our far most, like this is our foremost matter always whenever we are talking at any forum, any discussion, may it be research, may it be introductions into teaching. But we feel very good whenever we get any platform for discussing robotic activities, right? So I thanks to the organizers for this opportunity. So now I think without wasting much time, already 5 to 6 minutes late, maybe. Okay, it's yeah. So basically, I share my screen and let me know if it is done. So it is to be with our slide. Is it visible?
Yes, ma'am.
Okay. And second, I would like if somebody can, because in between when I'll go with the writing mode, then probably, or maybe up to you, you can switch off my video. Fine. One second. Actually, the light is coming. Yes. So, hello everyone, and today's topic is related to robotic kinematics. As I know your schedule, you have already finished discussed with Professor Ashokan the different types of robots and their importance, all the like kind of introduction to robotics. So now, before going to the kinematics part, I also prefer that rather than all types of robots, it's important that the manipulators on which the way we have shown in the picture, for the manipulators, let us introduce what is kinematics, why we should study it, because this learning, although many of you know it, that is why you have joined, still particularly about kinematics, what is the importance, and then what are the basic fundamentals, that is the methods of working for the kinematics. So I'll go this way. We have around 1.5 hours, but I'll use 1 hour 15 minutes. And almost there are three phases for my presentation, as almost mentioned. So I think first phase will take kind of 20 minutes, then 10 to 20, but majorly will put on writing mode when I'll discuss about the technique, so that maybe it should be as fundamental possible for you to learn. And there should be some takeaway today. Okay. So before moving, just introducing my, although you all are from India, you know where IIT Ropar is, but still this is one of the 21 or 22 IITs now. I myself don't count now, but IIT Ropar is well established with all its infrastructure well ready. In fact, whenever after pandemic you get a chance, it will be wonderful if any of you would like to visit here. This is the department, mechanical department, where presently I'm serving as head, and the entire infrastructure and the labs are wonderfully prepared. This is my just a small glance of my own robotics lab, which I call as Moyer, and this is on particularly on modular robotics, and we are trying to inculcate the idea of the because of the importance of intelligence, right? We are trying to inculcate the habits of inputting some kind of intelligence in all these types of manipulators. But mainly we work with the modular robots, like may it be any field. In particular, I always try to encourage all of us, wherever the platform comes, for Indian robotics, and that is why I had this particular MOU signed long back with the Tata Automation Limited, who had started with their Bravo. In fact, there are more than 10 big firms and many mushrooming firms for robotics in India, and I prefer that all of you may in your labs you should use them, so that only by uplifting our own companies it will be good. And that is why I also purchased Bravo, because rather than only the ABB or KUKA, where we do not get the opportunity of directly discussing with the manufacturing guys, in Indian robotic industries, it is always better that you can discuss what are their problems, which part they would like to improve. So you get some kind of input also you can give in the upliftment of Indian robotics. So Bravo, I had this MOU signed for a teaching skill lab in Ropar. So we are working on it. And this is just a small introduction regarding my research directions. It is about, of course, in any direction we go, particularly what I deal with. These are the keywords, and I say whenever we talk about manipulators, long back people used to say for repetitive work. When we say for the robot definition, we say one of the term which we say is repetitive tasks. Like robotic manipulators are used for repetitive tasks, but I work when for these days when things are so customized, when you are working with different platforms, different environments, cluttered workstations. So they're not repetitive, but you will get customized job which needs not to be repeated, which is for short term, to also improve the flexibility you need to have non-repetitive tasks. So this is something which I work, and we try to develop these using modular libraries. So this is my, what rest is just for your information. And what even if I'm working with medical robots or any job with defense, right, all, and particularly in industry, which my lecture is there in the last. I always try to see how we can develop a library out of it, like how to give a modular look for it. So this is how our lab works, and just few glimpse, small videos, because this is all just introducing my own self first. So whatever we do, I belong to optimization design of it. I belong to kinematics of it, kinematic analysis of it, and particularly till kinematic design is my job. And then we give to the dynamic guys. This is just a glimpse, because it is also introduction to kinematics, because this is my latest work in modular library and how we develop it. And this shows you that why we should learn also kinematics, those who are just starting and for improving their skills. So here you see that whatever robotic arms are available, we need for customized different tasks. Like we need for any given application and given task, which could be small or large, can we have some modules which can be assembled. So this is our latest work, which has gone into SME. So I thought of at least showing this to you so that you can see that how exactly we can work with such modules which can work at different DH parameters. And what are DH parameters, what are degrees of freedom, that is exactly what we'll be studying today. Yeah, so this is kind of manipulation. Of course, it will not be as rigid as our ABBs are. These are just the demos. But yes, we have done all the static force analysis, even the dynamic analysis is being done. So this is all prepared. This work is actually at robotic operating system. So I would say that robot operating system, that ROS, many of you may be knowing it, and or still not have good hands on like me. Like we are using it. I myself may not have a very good hands on, but I encourage the entire lab, my students, to use ROS. So this is what I would like to tell you, that even if you know only kinematics part, even if you are working with only the robot control, whatever is your area, may it be mechanical engineer, may it be electronics, right? It is important that you get introduced to ROS. If you are working with mobile robots, then it has a separate platform in ROS. And in case you are working with manipulators, it is separate. If you are only in motion planning or control, so you should use this system. There are further systems also, but you will understand them once you tell yourself that you have to use only ROS from now onwards. Then only you will be more globally ready. Okay, so introduction, because it was important, as I said, long back. Now these slides will match for few minutes, kind of 10 minutes, not match exactly. I mean, you already had got introduced to robotics, and now manipulators only. I'll talk about only robot manipulators, which are mainly the industrial robots, which you can say are the manipulators where the links are connected in series, right? And every joint is assumed to be a revolute or a prismatic single degree of freedom joint. So here, normally long back, as I've written, decades of back, people used to say robots, and whenever we write, it's when we used to write its definition. Then it was repeatability, which was important, may it be for dirty jobs, dull, right? These 4Ds we used to say. And this is all from the textbooks, like difficult tasks, very dangerous things. So this is where people used to start robotic manipulators. And you can say the job is from no emotions to precision. Like now the point is that you use the same manipulators for different reasons. And what are those reasons? Precision, as I have written, is one. So entire automotive for decades is using robotic manipulators. Even in India, although in India, if you ask globally, then the relatively we are almost at zero for usage of robots. Although you see everywhere, but if you ask any global person, then they may not know anything about Indian robotics. Yes, for the last half a decade, I would say half a decade. 1 decade, there was a growth. Half a decade, kind of 5 to 6 years last, it's emerging out very fast, very fast. So now we can see huge changes the way India anyway reacts. It's like once they understand the importance, then it will be, it is a revolution. So that is how industries are also speaking about that this is a revolution. So from automotive, although we were using even earlier, and electronic fabrication, yes, things were coming from large scale to nano scale and micro scale. This is separate. Now there are many other reasons why people are using robotic manipulators, and that is in environmental issues and chemical industry. Because of the environmental issues, chemical industry, rubber, plastic, it's not that uh, they are they are very big firms sometimes, but because of being keeping it less dangerous, for all these industries, robotic manipulators are used. So why I'm just referring these, because if it is so customized these days, applications are huge, then why not to learn what exactly is required by the industry if you join them. And kinematics is extremely important from that perspective. right? Because even if you don't want to design a robot, to run a robot, it is important that you should know its kinematics. And yeah, this is even important because unconventional designs, as I'm writing for the wood and furniture industry, there was times that at least wood and furniture were not using robots. Okay, for hygienic purpose, etc. Food had started, and now is the time for the wood and furniture. You might have heard of many of the YouTube videos you can see for unconventional wooden designs which are prepared using robots. So what you can do is, even if you are using a particular robot given by ABB company or KUKA 6 degrees of freedom or 4 degrees of freedom, right? But uh, without knowing its kinematics, you will not be able to work on it. You can work for some time by just playing on its keyboard, but still you cannot actually get into the design work, like design of wood, what particular aesthetics you want on the furniture. You cannot work on any specific, I mean, application unless you know its kinematics. So that is how I would like to say that it is important. And what other applications? Now, I would like to show you a slide where we have major applications which you see in use today for robotic, for these robots. Am I audible?
Robotic assistant.
Yes? Is it
Yes,
from
ma'am, you are audible, audible.
Okay, okay. All right. So if you see, apart from industry and warehouse, in warehouse I have shown only the mobile robots, but warehouses are extremely important in Indian marketing too, because you know that how the one company I talked about, Bravo, another is High Tech, which is like which had been started I think around 15 years back, and now it is one of the biggest firms in Indian robotics, who are dealing with providing different solutions to the warehouses, robotic solutions. So these are kind of mobile robots, but I'll talk about the mobile manipulator, because all these things, for example, this one in defense, the left side above, I've shown a picture of a manipulator which is attached to a mobile base, right? So this is also important. You can always consider the mobile system separate. You can do its planning, motion planning separate, and you can do the motion planning of the manipulator separate, the serial manipulator. So why I've shown you all these applications, there is a reason, because may it be in service, may it be in agriculture, or nearby, even at the right side below, you will see that we have these buildings get work being done using assistive devices which have its major part as a manipulator, serial manipulator. And then even in medical, you know that Da Vinci is one of the surgical system is imported, right? We have not yet developed at India any system which is already in use for medical, I mean, surgery. But yes, there are many who are at the final stage, right? But as far as the reference is concerned, you might have heard of and you might have seen in larger institutes like this, even PGI or Medanta at Delhi, they do have these robotic manipulators. So now why I'm showing this particular slide, because we would like to extract out of it one common thing. These are applications are very distant, different, right? But what is to be extracted? You will see one thing which is common. Of course, robot is common, but in that robotic application also, the common part is the configuration of this robot, right? You have seen many applications in your previous lecture, but now you will see that here we are talking about one configuration, and that is the serial manipulator, where each link is connected to the other link using any joint, either normally they are revolute or prismatic, and all the joints are connected in series, or all the links are connected in series. So this is called as serial manipulator, which has its base fixed and rest of the links are connected in series. So now if you'll talk about this manipulator at the left side, which is not whose base is not fixed, but its base in the assistive devices of this building or in defense, these examples show as if the base is also moving. Yes, it can be, but then we say it is not a manipulator, we call it as a mobile manipulator, because it has a mobile base which you can study as a mobile robot, And manipulator, you can you can always consider its base to be fixed as the reference on that particular mobile platform, and then you can work on the rest of the degrees of freedom. So how to do all these things, what does that mean? This is what you will be showing, we'll be discussing today more. Okay, so basically, this was the introduction for the robotic manipulators. Little more in that now to show to get its, because if we are talking about the kinematics, then there are few terms, there are few aspects and features of the robotic specifications which come into existence, which comes in our discussion. So tell that, I took a few examples of the very advanced recent robotic manipulators which are out and which are in use for different applications. So this is my another way of discussing with you different applications, because here I'm not even sure, because normally in these courses not everybody is from the same field, right? So people are from mechanical, electronics, computer science, and some are teachers, some are at the very beginner stage of their teaching. So because of such audience, I prefer to share with this that sometimes you know about the specification, sometimes not, right? So out of this, the first important specification whenever we deal with any robotic arm is degrees of freedom, right? So we will write the kinematics. What is kinematics? I'm coming to that later. And these are the important specifications. Now, what are those? For any given robotic arm, this is now a manipulator. So I'll talk about manipulators in this particular 1 hour. So degrees of freedom are how many, because degrees of freedom, what does it mean? According to that, we know that it is the minimum number of individual, independent parameters which can define the motion of a particular or configuration of a particular robotic manipulator. So that means you need some minimum number of independent parameters, which even if it is taking its, like it starts moving, this particular robot may start move. So what are those minimum number of parameters which will define that at what configuration or posture it is at present, right? So degrees of freedom are, for example, in this are six. All are controlled. Payload is what capacity, what weight it can carry at the last end effector, right? And mass is its own weight is given, and reach is like the maximum reach it can extend itself and actually reach, right? So these are okay. If it is so, why I'm showing you this, that means this type of robot, which is now from Fanuc, which is called as cobot. Now cobots are just because such robotic manipulators which can work in presence of in cooperation with a human, right? That means it has a extra feature of safety. In fact, these days, whatever robotic arms are coming, they all are actually having this feature, that we are working with cobots more, even in industries, particularly those who are into small scale where robot and the human have to work side by side. There you have to use cobots. Well, that is not the point today. So why I would like to show it is that from here this will be used in some industry, but now I come to its comparison with one more robotic arm, which is small sized industrial robot. So common things, common are, this is also another robotic manipulator, which is serial. It has degrees of freedom 6. But look at its payload capacity, 0.5 kg only. And what was for the previous? It was 35 kg. That means there is a huge difference. And the huge difference, you will say, oh, it is related to its mass. Of course, it's here it is mentioned the mass as 990 kg and another is 4.5 kg. Of course, because the capacity was less, it's a very small size robotic arm. According to the application, the customized thing is different. And it's not about only that which, because we start with, oh, it is a smaller one. So that means from our side as a designer, the smaller, small sized as well as very light actuators will be enough. But I would say that before talking about actuators, before talking about which actuator will be used, we have to think about even the size is according to the requirement, and size comes from the kinematics, because this is all what length, what will be the angle, what will be the size of a particular manipulator, even the width, this all comes from kinematics. So now next, so So it's, of course, I'm not getting into the applications of such small size, that I'm just writing for you to read later. Third application, this is a mobile manipulator, right? Now, if you say, I'm just showing it, that here, if you just check it, uh, this part, if I take separate, right? Then you can say that for the upper manipulator, we have 1 degree here. It is mentioned as 5 degrees of freedom, but you can always see one is this, second, third, fourth, and five. So basically, it is talking about the 5 degrees of freedom of the manipulator. The 2 extra degrees, which are for moving in the, or if it, even if it is just one, because it has only one actuator, but it can go in the plane. So you can say it can take turn, right? So that depends if it is single or double, because according to its manipulators, it will be maximum 2 for working in this plane. So that will be added. But only for the manipulator, you will find that it is a manipulator which, when you study, for example, you get to know how to write the kinematics of a manipulator, and I give you this particular robot, then you can always take this particular section out, work on the manipulator separately, and work on the mobile base separately, right? So whatever is the requirement, accordingly we can work. So this is all just to introduce you to the latest some of the recently coming configurations, so that you get connected to what you know is also getting used in the recent industry robots. So this is, again, this is only for paint, right? So if it is only for paint, that means only what position it is here. Why I'm showing is it's a high performance, but what is the performance? Apart from the dynamics, like which velocity and can I reach here, what are the torques required, that everything comes, and then how to control if it will maintain at that speed or not. This is coming to the dynamics and control. But as far as its kinematics is concerned, now I introduce, it is like if you want to paint, and this is your present configuration, next is say this, right? After some time, say it is this. Then after some times you want it to be something different, right? So where you have picked up this gripper or the tool which will be used for the for that industrial application, that how it is connected to the base, how to show that equation, the relation between this end effector xyz orientation, and with respect to this frame which is attached somewhere at the base, right? How to connect all these things, because we have so many degrees of freedom, plus the importance of the degrees of freedom will boil down to a particular equation which will call as the kinematic model. We are coming to that. But this is all to show you that, see, different manipulators, what is common in them is the same configuration. Everything is having a serial link, a joint, a link and a joint. So although its payload capacity is 25 kg, now here you will find that with the almost similar kg, its own weight is not mentioned, but I think next it is mentioned. Anyway, I'll just show you this quick picture, which is also a collection, because I like this video. Of course, it is from ABB, and it is talking about, I don't know if you are getting the voice. Well, it is not so important.
Yes, come.
Okay, so basically why I showed you this is, this was all about the introduction, not only to the robotic manipulators, but also to the importance of robotics, to the introduction of kinematics. Because the applications which I just showed you, for example, this last video is also being added to tell you that it's the same manipulator, one of the manipulators, which is serial in nature, right? And say it has 6 degrees of freedom, and you will see that, okay, the skilled workers, once they know how to use it, they will start using it. But unless they know the kinematics, because not everybody can actually study it. But when engineers help them to, whenever you need to, plan them again for a new application, you need to know what are its degrees of freedom and how. You need not to have the experts, because till now, till the last 1 decade, people were working with that. They have taken robotic things for their help, but I mean, in their industry, but they have no idea. They have no clue of the models at the back, and this is why they're always dependent upon the firms, even to plan the new whenever they are working on a new application. So do you think this is applicable? I mean, if you are working with the customized robots, you are changing the flexibility is too high, you're changing the application every fifth week, then how can you be relying upon the firm to actually plan for you? So basically, more and more engineers are these days being hired. Even in India, the robotic firms are increased, and even if it is not the development, but I would say the employment is almost getting high. So people should study robotics. At least this kinematics also help, because just one line, the applications which I have shown, every application is for a different environment. But what is required is the three words I can give. One is where to position the end effector. That's why. So I just showed you that in the end you have different tools. You may have a gripper, you may have something, something to be picked up, or some magnetic one, right, for the glass. You may have at the end something is connected, but then where to position that end effector is the issue, and how to orient it, because you might have seen it has positioned at the different end effect at the different point, and after that the orientation will be changed. So everything is about position and orientation, and also what are the rest is related to the kinematic model, because how many degrees of freedom it has, according to this only you can actually apply it for some application. So this was just for the introduction, so that we should be ready that yes, whichever book you follow, today's introduction, but you should actually cover this in a detailed mode later. Robotics in India, this is also for adding up in the importance, because as I'm already speaking about the current status in Indian robotics, so I this is just to share with you a few news, like from the last kind of 2 to 3 years, how we have seen. That is why I said half a decade, right? So since when thousands of crores the industries are putting up, because they have seen the importance of, they're calling it revolution, right? So as I said, revolution is there, and now Tata Bravo is not called as Tata Bravo, it is actually BRAL. It is BRAL, right? So Bravo Robotics Automation Limited, something like that. But of course, it is from Tata, but they have separated this firm, right? So anyway, that is separate, but we do have Indian manufacturers. We have many another manufacturers, like you might be knowing many names, right? But this is just for example. I am not here to just talk about this agency, but similarly, we, as I said, high tech. So these are just few news, and they are also not only for autonomous vehicles. They are as I said, they started this company like as an enthusiast who wanted to work in robotics, right? But yes, this firm is really big. So you can see how the bigger firms are coming up. Upcoming businesses are too large, and this is why your learning in robotics course and these courses are extremely important for your knowledge and for you to tell your students about it. And as far as humanoid robots, okay, I'm talking about the boon of robotic startups, because these days, yes, there is a boon, mushrooming companies, but you never know which company will really come out big or small, but everybody will contribute. This I'm sure. For the time being, those who would like to get into robotics in a proper way, sustain themselves for a few years, they will really that will really be good. I mean, I would say from both perspectives, from the Indian robotics in total and for the firm in itself. Okay, so this was all about the importance. Now, let us come to the fundamentals and the techniques, because what are robotic? Because some of the, before getting into what is robotic, robokinematics, these are a few, terms which we normally use, and they come from, as I said, I'm not sure if all sitting here with me are mechanical engineers. So joints and kinematic pairs are again inside joints. You always have, I do not have pictures here, but you always have a revolute joint, a prismatic. So you can always say that how, for example, our arms, our shoulder is kind of a ball and socket which has more degrees of freedom, but our for example, our elbow has only 1 degree of freedom. So joints are different types, right? This is how you can understand. Then you come the kinematic chains, because how we are talking about the serial manipulators basic structure. So from one joint a link is connected, another link is connected with and when you are connecting these links and joints in series, you get the kinematic chains, right? And you can always found there are always some methodologies to compute how many degrees of freedom it has. It is not that by looking at that you will start counting it. You can do it, but there is a method. So whenever we are working in a group or in a team, people who are from electronics or controls, they must know these terms only, but for their detailing they should actually have in the team a mechanical engineer. So this is, I always believe in the interdisciplinary work. And end effectors I've already spoken. This is actually the tool or any gripper or the particular component which is attached at the end of the serial linkage, right, of the economic change, which will be used for the particular application. So this is what you would call it end effector, right? And then of course it will be using some actuators and drives, that is separate. So these are just for introducing some of the some of the terms. And yes, now from here, I would like to use a little bit of pen writing also, because importance is that we talk about linkage, right? We said, okay, I'll just fold. You may please stop the video, okay? Yeah, so we were talking about that we have a particular linkage. This is base. Now, whatever I have introduced till now, I am using it. Fixed base, any link, joint, another link, joint, and this joint is say to show you that this is a revolute joint, right? This is another revolute. Say now I show you a joint which is prismatic, which means to and fro, like your piston, right? This is like the hinges. And then after that, we have nothing but a gripper or the end effector. Now, even if it is this is not a plane, because here it can be shown that this is a planar, but the moment I just change its shape and I say no, the first is fixed, but it can rotate like this, its axis is this. And here the axis was this, and this was fixed. This was fixed, and this is the Z. So there's a difference now, but this is also similar. This is rotating, and after that we can say that we have something which is, it has just taken a shape like this. This entire is same link, which is rotating, right, about this Z. And after that you have another link which can rotate like this, and then this particular is P. So this is also R, and P. So first is a rotatory joint, but this is a spatial. Spatial means which is working in the space, like where you need a three-dimensional background for showing or for actually denoting its position and orientation. And this is entirely, the entire mechanism is in a plane. So these are important, just basic terms. So this is a planar in which, because it will not change its plane, it can change, it can go here and it can go here, right? Or it can move ahead, because this is to and fro. It can be fixed here, but it will be just going up only here. So these are the different configurations. So we are talking about configuration as one word, and posture as another, right? So whenever we are talking about posture, that means I'm talking about these different postures. Like this is one posture, second is in which I can say that I have changed it, okay, right? Then this is another posture, or it can come here like this, right? Similarly, this will change, it will go at the back. It can go even at the side because it is rotatable. It can come at this side and the rest part can remain. This is just the same linkage and this is one gripper. So these are different postures, but as far as this one and second, these are called as configurations. That means this basic configurations. To introduce that, I would like to say that coming from the basic terms, how we say that even if something is 3 degrees of freedom, both had 3 degrees of freedom. It has, even this had 2 revolute and one prismatic joint. Even this had 2 revolute and one prismatic joint, but and both are 3 degrees of freedom, but both have their configurations separate, right? And these configurations are also, so these are called as, some of the configurations are very known, are called standards, which one should study in the beginning. And I used those only, and simultaneously at the right side, using our writing, I will tell you all the fundamentals. So here the takeaway is this, what is configuration and the postures, which means at the different, when you are changing the any degree, you get a new posture, because the degrees of freedom help us to define the position and orientation. We are coming to it, what is position and orientation. So particularly we have just, as I said, the takeaway is these two, and from here there comes the basic configurations. Now SCARA, it has a specific set. In fact, it has 4 degrees of freedom, but the basic manipulator, the first 3 degrees of freedom, which defines the position, because I'm coming to some of the examples, but these are kind of defined as RRP, means revolute, revolute, and prismatic, or 3R is like your arm. So your arm, if you do not get into the complications, because your joint at the elbow or at your shoulder, it has 3 degrees of freedom. In fact, it has more than three, five, to which it can actually take, but we are not getting into the nitty gritty. So basically, even if it is, it has to be considered similar as a ball and socket joint. So it has 3 degrees of freedom. But in a particular plane, if you are working for an arm, then you can say that it has RRP, like all the three revolute, revolute, 3 revolute joints, one at your wrist, one at your elbow, and one at your shoulder. So you can say it is like that, anthropomorphic configuration, spherical. So rather than speaking it here, this was just to show you how to donate, how to the notations, the notations being used, how to denote, right? So basically next is, this is one example. Now from here, configurations are being shown to you, but simultaneously we will be taking care of some of the kinematics importance. Now what is there, what it can do: up and down, left, right, in, out, right? There are 3 degrees of freedom. Okay, 3 degrees of freedom. Specifications should be very sure that what we are doing for its kinematics. What are the types of joints, which means PPP. Now these all are prismatic joints, and if I, this is the gripper, and what is kinematics. Now here I'll introduce the kinematics. So if now you tell me, taking any example, what do we mean by kinematic model? Why should I study it? We need to study it because we would like to have a relation between the end effector, which is this, in this case, position and orientation, and base or a reference frame with rest reference. You can simply write that. That means something here. If I have a reference frame here, and if I say, as it is being mentioned, like we say x, y, it said x, y, z, and this way, so I'll take this as x because we have to keep the right hand rule. This is y. Okay, it is in fact other way around. If you want this way, then the z has to be above. Yeah, it was correct, right? So if this is a reference frame, I would like to know if there is a point here. You need a reference point even at the gripper. Now, how to tell that what is the position vector of this particular point? After some time, if you say this is my first degree of freedom, this is second, and this is third. Say in the third, and this is called as first D1, D2 is the movement here, and D3 is the movement here. So I'll denote the prismatic movements as D and revolute whenever there is a rotation as theta. Okay, so if it is so, that means we have here d1 in our as the parameter, d2 is another parameter, and d3, which are variables, and if they are changing, the configuration will or the posture will change, right? So this is to connect whatever we have done till now. So if it is so, you understand that if I change the posture, even if only D1 changes or D2 or D3, this point which is mentioned here, I call it as the P, last point for the end effector, right? If it is so, then the position will be defined based upon D1, D2 and D3. That is all right. Now, in this, even to show, because the orientation cannot change unless you rotate it, right? But you this orientation is fixed in this case. And normally in the 3 degrees of freedom manipulators, normally they are used for positioning. The configurations are different, but normally they are used for positioning. But in totality, the relation of this end effector position or even orientation, right, if it is available with the reference frame, how to connect this, how to join this. Now, in this case, it is very simple. You will say, we know that in x direction, right, the movement is, say this is 0 here and it is d2. So you can always write that I can write this vector according to my, in x, I can in fact look at this and try even now. And it's very clear, we do not need anything very complicated here, right? And you can always see that if this is zeros here and what the movement is only from here, movement is here, and movement is above is from here. Looking at the references, I can always see that d1, d2 denotes my x, d1 is for z, right, d3. So we can say in z, in my x direction, which is now I'm working with blue, in x direction, it will be say positive in that direction minus this d2 if it is moving in that direction, right? And in y, the second component is for y. So y is how much I'm coming here. So actually, this is not mentioned according to xyz. The value is what I've shown as d3 as positive, and z is how much I'm going up. If this is the way I've defined, because reference frame can be defined either way. If you change the reference frame in a different format, of course, your values will be different, but this is how we can always show that this vector can be defined. It is very clear. So that means we have got to know that the position vector in the form of, so you can always write it is d2x plus d3y plus I mean x, or you can say I, j and k, if not x, right? This is so straightforward. In fact, you do not need any kind of anything which is required to be detailed. But this was just to tell you the introduction of kinematic model. That is the takeaway for this slide. And one more thing, and that is work envelope. In case, what is work envelope? Work envelope is like what are the total number of points which it can reach, like the set of all the points where the end effector can position, can reach. So we are talking about not dexterous, but the work envelope. So it can reach according to, if I ask you like what will be that shape of the work envelope which will be formed if you can change all the d1s, d2s and d3s, because it can go here up all these directions. If I just change the color here, then here up and down it can go left and right, but depends, like, you know, according to the constraints, it will make maybe more in this direction and less at the back, more in this direction, less at the back, more up and less down. maybe something, I'm not getting into the details, but yes, this will be the work envelope where probably this particular point, which is the end effector, can reach and work, right? It will be certainly smaller than that and it may be hollow in between, but that depends. It need not to be hollow, but it will be at least it has constraints. It may not be able to go down than this or upper. So that depends upon the limits. And this will be the approximate shape of the work envelope. So this is the takeaway for work envelope and about the kinematic model. So next, taking one or more example on the configurations. Now this configuration, we come back to the degrees of freedom. Again, 3, because 3 parameters will be required. The degrees are, first joint is revolute. Now as we can see here, prismatic and prismatic. And here, this is P, revolute and prismatic. Okay. And this is one of the, again, basic configurations called as cylindrical configuration, right? In fact, the previous one sometimes is called as cuboid or box, right? Because of its work envelope. And here, as the name suggests, its work envelope will be a cylindrical form, not really a complete cylinder, but it may depends upon the limits of these particular joints. Okay, so what next? We have already understood what is a robotic, what is a kinematic model. So without again getting into the any specific technique, if I try to write where this particular point will be positioned with respect to a given frame here at the base. So this is, see, the base are always fixed. This is what we have learned about manipulators. This is fixed, this is X, Y, and say this is Z. Now, if I want to define this particular point, then how would you like to go about it? Say this vector, right? Would you be able to write it? Yes, you may say, can you write what is the X, Y, Z, this point P of this point? This is a spatial manipulator. Again, 3 freedom, spatial. I'm using all the terms so that at least there should be some takeaway today. You know, all these things help you to take the full course. That yes, it's very, very easy and it suits you and you should study a full course on robotics. So here you can always write using the geometry because if you work only in the XY plane first, you can see you can see that how much if the height is according to what you have in the Z. So Z will be related to, say, my first is the theta, second is D1, and third parameter is D2, right? So theta will let me know on this, in this XY plane, how much is from here. So if you say this is the line, so we can always check it according to, if first of all we have to see theta with respect to what? With respect to X normally we take, right? So if it has rotated already this much, right, that means we will be able to write in your X and Y, that means in the form, what is X and Y? You have either cos theta and sin theta, something like that. And then third will be your height, which will be given up by your, in fact, one height will be directly, I'll be showing it for the third term, that is Z component. I'm just telling that without knowing the techniques, you can try using the geometry and you'll be able to write it, right? And for the Z, it will be, say, second P, which will be D1, right? I'm not showing you the details, but here, as far as this D2 is concerned, that is this, where this will be added, this will be again added in your X. So somewhere your X component will be dependent upon your d2, which means this, right, as well as your theta, and y will be also depending upon both d2 and theta, because that this will be taking turn, and from the geometry itself you will be able to write the vector or the complete. These are called kinematic model. What is kinematic model here? The relation between this particular point P and this reference, how you are able to define here. At present, we are talking about just the position. And position is defined using how to define X, Y, and Z of it. And these will be, now I'm writing, why I was writing in these forms and not exactly the values, because I want to tell you that they are functions of, say, theta, D2. In fact, sometimes in this it is not, but it may be be a function of d1, right? So here I'm not writing because we want to say that it will not be. Similarly, this say, right, and this will be a function of say d1. But in totality, now I'm writing the same kinematic model in a better, more defined fashion. So what is a kinematic model? Kinematic model is your function, how you are connecting the set of functions, or you can say a vector valued function of your uh, either theta or d. We call it as generalized coordinates. This is your kinematic model, and you connect it with x. So this is what you study in your books, because we cannot every time tell, this is a theta, this is d and all. You'll always say there are 3 degrees of freedom. So there is a vector. This is the takeaway now. Q is my generalized coordinates. What do we mean by generalized? Means it can be any units. In a simple way, I'm telling you, because we studied in multi-body dynamics. But given any units, right, now any parameter from any domain, if that is being used as a coordinate, like to define the configuration at the last, then that will be general in nature, and we call it as q. So q can be theta, it can be d, right? It can be theta or d, but how many number it will be? The number will be number of degrees of freedom, right? And that means number of coordinates. So that will be its order. So q will be having, in this case, it will be a function of q1, q2, and q3. There are 3 degrees of freedom. Of course, your first is theta, second is d1, and third is d2. That is separate. So how to write it? That means you will get a model, and what is x here? Capital X, right? Or you can say a bold X, the vector. So these are vectors now. This is a vector valued function. That means a set of functions. So basically, if you connect this and connect these, you will get your model, which means capital X is equal to a big X, and writing in the first function, second function, third function. So this is vector valued function. So I think from the basics itself, I'm trying to tell you in each slide some of the steps. So till now, what is new in this particular slide we have seen is the writing in the journal mode, and that is this kinematic model. Now, so far, this particular configuration was concerned, you can do from the geometry, right? But we have to come next, because this half an hour, this is important. Quickly, we can see that, okay, this is another like your arm, as we say, and this is an RR. Oh, this is not like arm, RRT. Here also, wherever this particular point, you can take any reference point. Point needs not to be different, and say this is your fixed somewhere, or this can be connected to any mobile base. That is different. You can add those movements and say this is your X, Y, and Z, and then how to connect this P. That will be, now every time you cannot work on, because these things are very straightforward. You can always see what is theta here, and what is the this much distance, what is the different distance, and you can always write the function X, function of theta, because here also it will be theta 1, theta 2, and D. Now you agree, because function of Q1, Q2 both are thetas, and Q3 is actually a prismatic joint, depend upon this, right? So first will be a theta 1, second is theta 2, and third is this D. We call it as D3 because it is at the third location sometimes. This is just the name. So I think so far I have tried in some less time to tell you what is going on, what we are trying to compute, so that even if you get little less about how to compute, that is there in the books, but why to study and how easy it is, that is what I try to show you in the different configurations. So this is again another configuration like your arm, as I said, RRR. So here you have, in case if it is a class, I could have asked you, but now we are working in an online mode. So here you will say it is, your function will be of a Q1, Q2, and Q3. Both three are thetas. You can write theta 1, theta 2, and theta 3. So this is a function, and x will be x, y, z. So your each point at the end effector, say this is your point, and how it is connected to say some in the frame here, that will be shown through this theta 1, theta 2 and theta 2. So this was all about the fundamentals. Now going ahead, number of degrees of freedom. This is the Skara robot. It has 4 degrees of freedom. So as it is said, now it is being added. No problem. The moment it is being added, it is very different. Going back, I have to just tell you that their workspaces are different. This will have a spherical workspace, work volume. This will have a cylindrical work volume. So that is not bigger part of kinematic, but this is just to complete for the sake of completeness. Now I tell you that this is extremely important that whenever you are working with a point, at any point, it's not about only position, but it's orientation also. And if you want orientation also comes into picture, more than 3 degrees of freedom will be required in a spatial working. So that means I have this, and rather than only a point, because I was taking just a position vector till now to tell about the end vector, right? Now if I say that it can go up and down in this case, but rather than that, I'll take quickly. Oh, this was just for you to tell that this is, yes, even in this the configuration can be changed. You know how? For example, please pay attention here. So this is like this, but if I change this particular third, so say we can say this is my theta 1, theta 2, theta 3, and up and down will give me a prismatic joint. That is maybe D4, right? So up and down it will go, but the moment it is rotating like this particular thing will look like a different orientation. Hope you will agree, like this, right? After some time, it could be even more rotated and it will look like it can come even like this, right? So the orientation in this case can be changed. So rather than position, you would like to show its orientation, and that you can show through the transformation matrix only. And this is, you need to assign a frame everywhere. Those who are into mechanisms or multi-body dynamics, they know that to define these links with respect to each other, you do not need only points but also their orientation, and that everything is possible through frames. So I introduce to you quickly, because the time is short, the frames, right? And frames means whenever you are talking about how this particular frame, the last frame, can define with respect to the base frame. So I will make for you different frames. This is a reference, okay, this will be fixed face. Second is like it has done for this. Third, you will join here. Fourth, you will have for your, like, this is for the first link. Second link is this. Say first link I'm taking here, second here, third here, and fourth I'm taking here. Right? That depends. There is a specific way what you study in robotics is how to affix frames. So I'm writing it here. How to affix. So study about it, like frames. But even if you take them arbitrary, it is okay. We do not take them arbitrary, and there comes the importance of my last 25 minutes, and that is our DH parameters, which is the technique, which is one of the parameters. In fact, there are people in the global sense where people are saying, no, I don't want to use robotic DH parameters. But I must say that in the beginning, when you are studying it, for a majority of tasks, DH parameters are useful because they're applicable in all types of these configurations. And even if you're not working with robotic manipulators, they are very helpful in any multi-body system, even in automobiles or so, right? So what are those? To come to that, importance is about these frames. So it was easy for me to fix a frame here, and then within the frames, with respect to each other, can I define rather than a point, because point I could have defined only by a position vector like this. But do you know, I'm writing a big question here, how to um, define orientation, right? How to define orientation. So orientation, I mean, frames are fixed. Why? So that we can define orientation. Because orientation can be defined by, I'm sure you know the three angles, the way you know one possibility. First possibility, for example, is using your Euler angles. I'm not getting into details of it, but just connecting, because you know, particularly people from mechanical engineering, they know, and even otherwise in the ship when it is rotating, you know that we talk about that it has a roll, it is rolling, or it its pitch is changing, right? or it has different yaw. So roll pitch yaw you might have heard of, or in gyroscopic you might have heard of, like, okay, it has a spin, it has a nutation, right? So all these words are actually for the Euler angles, which means three angles. We call them alpha, beta, gamma, just to for you to quickly understand which are required, how much about x, y, and z you are rotating, so that this frame, say this frame has this xy, this y, and this z. I'm changing color here just to show you quickly which one, say this. Okay, so say this is my x, this is y, and this is z. But what is the difference here? I may not have the same here. Maybe my x is here, this, right? X, y is this, and z is this. Can I write the two with respect to each other? Yes, and this is what we study in the transformations. And here I'm talking about the importance of matrices, and particularly the orientation matrix, because orientation matrix, the second way of writing is through a matrix form, and we call it as a rotation matrix. Right? That means rather than one column, you need three columns for defining not one vector. Earlier, what we were doing was we were writing only the position vector directly in the form of x, y, z in this reference frame. Now you'll write three vectors, x, y, and z of the end vector frame like this. If it is so, how you will write? You can always say, in fact, here I can write directly for you, because, but that part we will not be able to cover here. And it is like this x, which is in the z direction. I know it's, we can use the direction cosine. So what I'm using is direction cosines. And if you see that details of transformations, then you know there are two or three methods which are very clearly given, easy to understand for orientation, or to define the orientation of one frame with respect to another, right? So if we are using direction cosines, that means the cosines between the two vectors. Say I'll take x with respect to x of it, y and z. So this x and this x are 90, so the cosine will be 0. Then this x and this y, right, it is also 90. This x is matching with z, so it will be 0, 0, 1. Basically, what I'm doing is I'm writing in the next page. So given any configuration, say even in this, we can write the rotation matrix, right, which is defining the orientation of any frame with respect to another. You know, matrices are not used as operators only, they are also used to represent orientation. It's not that always you need three angles to represent orientation. The orientation matrix helps us there. And how, using the cosines you are using, you will say x of end effector, x of end effector. Okay, one second. Hello. uh, it has closed, maybe one second. One second. Is it being shared again?
Yes, ma'am.
Okay, so we have next last 15 to 20 minutes. Here we see that I just write again, because okay, that is discarded. I wanted to share with you. By mistake, I discarded. Anyway, this video will be shared. So basically, what is required is I was talking about the importance of rotation matrix, which is helping us for two things. One, as an operator, which you might have seen many times, because if you want to rotate anything with respect to theta in transformations, we know that there are specific matrices which can be used for that. But I'm coming to it for I'll show it there. And second is for representing the orientation. I'm connecting it to our present understanding that what is kinematic model, in which you are somehow connecting your position and your orientation of the end effector with respect to the reference frame. For example, this is 6 degrees of freedom. Another extremely useful industrial configuration, right? The Puma. So Puma is actually about the configuration because it has 6 standard beams all R, 6R as it has been written. Now, how to define this point? Now, whatever you try hard, it will be very difficult to use just the geometry and write this position and orientation of this particular last thing, right? For example, this is my orientation of this, and this is my fixed frame here. So in the last, I could have used using the direction cosines because I was writing for the direction cosine. It's easier that, but for that you need the cosine angles between the two vectors, the cos out of it, that is the dot product, and that is what I was writing. Orientation using direction cosines. One of the methods I'm writing, so because it was at least one method to make you understand how the orientation is being defined. So it is, we have x of end effector, y of end effector, and z of end effector. For example, here, I'm just changing because there's so much red here. So here, right? So it is like, so this is my x, y, and z of the end effector. Last one, that means the sixth, right? So sixth. So this is my z then. So this is y approximately. So basically, in that, these are E are depicting their end effectors frame, and reference frame is say this x, y, and z without any subscript. So basically, we have to see how the two are connected. And if I try to write a rotation matrix which is defining the orientation of end effector with respect to fixed, then it can be written directly using direction cosines, and that will be xe. I'm writing for x first, dot x, xe with y, xe with z, dot products. Then ye with x, ye with y, x, and ye with z. Then ze with x, ze with y, and ze with z. This is what I was doing in the last, when quickly looking at one second. Looking at the last picture, when okay, those have gone, but I can write directly. So in case I say that I have to write this vector and this vector, so this is my x, y, and z. And in the other case, I might have taken, so this is z here, but here, although this is okay, the z I would like to take here, but maybe I've taken, although I will not, because joint is this axis, I'll take the z again in the same direction, right? But still, in case I take this as z, and this is x, and this is my y. Say, the frame for the end effector is this. Then can I write using that direction cosines the rotation of end effector with respect to previous? Then yes, you can define the frame orientation of this frame, the last with respect to your base, as using the direction cosines xc with x. It is exactly 90. That is why it will be 0. And then your xe with y is 0 and xe with z is 1, right? Because considering these two as the unit vectors only. Similarly, if I write for the y, the second column you will find that it will be this. And the third column, which is actually aligning with z, right? I purposely do it so that I can write fast for you. It will be this. So quickly you can write using the direction cosines, as I've shown you the formula, the orientation of a particular frame with respect to another. So in totality, you would like to know in the kinematic model how to write my x, and this orientation can also be converted to alpha, beta, gamma, the Euler angles. These parts are done separately, but presently I'm not just showing you because this will be huge for, of course, not in one lecture, but I'm connecting you to the things which will be used, right? So if the orientation can be represented using a matrix or using these three angles, but they can, I'm telling you that the two are interchangeable. You can convert from angle presentation to to matrix, or matrix to the angle. You can convert that. So once we can, that means my end effector finally will be able to show that whenever we are working with any specifications or the last, given a 6 degrees of freedom, I can say that, okay, in a space, my end effector will, a large will not be only x, y, z, but it will be xe, ye, ze, alpha, beta, gamma, which needs to be connected to a function which is made up of the degrees of freedom. And this specifications I wanted to show that whenever you are working with even the practically you are purchasing a robot, these will be the basic specifications and you will be working on the degrees of freedom. Of course, repeatability and rest of the things are separate, but presently related to kinematics, you will see that, okay, for example, this is for the Bravo 5 degrees of freedom. So this is first, second, third, fourth, fifth. So this will be for my Q1, Q2, Q3, Q4, these are the ranges known. Speeds ranges maximum this, right? So these specification cards are also very straightforward to understand, and you have a function of Q which will be connecting to your X with your X. So this is the meaning. Now, finally, I'll just show you one important slide where the importance of DH parameters are coming into picture, because I just showed you a specification, and there I said that even if it has 6 degrees of freedom or a scala which is 4, it is not easy to write its geometrical to write for its geometry, sorry, using the geometry to write its model, right? Then what does we do? Idea is we have DH conventions, and I'll just quickly show you how easy it is. What it does, that I'll tell first. For example, this case study I've taken from some books. Now I'm connecting you not only to the specifications, not only to the textbook, but take any research papers whenever they are working on the kinematics of a particular robotic arm. That means it will be talking about normally DH parameters or the transformations. So those who are interested in this direction, they must pay attention into the transformations, Euler angles, orientation presentations, direction cosines. I've already talked about these things, the importance of it, and finally the Denavit-Hartenberg parameters. That is a full name, from the scientists, there are two. And this will give you, I showed this example first so that what we are talking about, it will be a tabular form, which will have, you will see A, alpha, D, and theta. How many? 1, 2, 3 in this, 3 in this. What is these? These are according to the degrees of freedom. This was a DH parameter for 3 degrees of freedom. Some robot, which is shown here, right? And in that, every pair, each pair of links will have will be defined through 4 parameters. Each pair, right? So that means from link 0 to link 1, link 1 to link 2, link 2 to link 3, and link 3 to a virtual link 4. Right? So 0 to 1 a pair, to 1 to 2, 2 to 3, and 3 to 4. 4th is virtual and 0 is my fixed. This is the end of it. I think I've tried to connect all the terms, particularly for beginners. And from all these things, you will find that you will be able to connect now 4 parameters each, and total you will get the 16 parameters for this, which are this: alpha, bit A, alpha, D, and theta. Now the only thing which is left for today's lecture is what are those 4 parameters and why these 4? What does that mean? What is happening? Basically what it is doing is it is going stepwise, defining a particular reference frame at the base. It connects it to the frame connected at the first link. Then the 4 parameters will be used to connect that particular transformation with the second link. And that means if you have 3 links, then every link will have, now I'm writing this collectively with the next, okay, I'm not showing this. This is just quickly to show you that there are unconventional values also. You know, even for Raven 2 or Da Vinci robot, if you are working with in medical robotic lines, the same knowledge of DH parameters or kinematic model will be used. And Raven 2, you do not have the 0 and 90. The alpha angles will be even non-conventional. But asking you to learn this now. This was just to tell you the importance that once you know how to write them, then it's just the matter of frames, right? And that is even if it has been shown here. Finally, the DH conventions. So here you will find that what are those? If we are talking about each pair, and each pair of link, not 0, 1, 1, 2, I'll take I minus 1 and I, where I goes from 1 till n. N is your, as I said, number of degrees of freedom. Cool. So basically, between the two, if I get four parameters and the then what it will do, from I will actually these four parameters will do. These four parameters will actually help us. Four parameters will actually help us to denote the ith frame to the I minus 1th frame. Then what it will do? In totality, if you know pairwise pair, then you can work with multiple bodies. That's the gist. That's the gist of multi-body systems. Wherever you are, this is I minus 2, this is the I plus 1, and I'm taking just out of that one pair, say this, I minus 1 and I, which means this is the pair which is connected with, this is 1, this is second, two joints, and there are further joints, right? Further joints, and say these are joined with some link. So I'll take this particular part and show in front of you what is the meaning of these four parameters. Once we have those four parameters, there is a standard matrix in which you can put these four parameters, and that matrix will give you the matrix of transformation of I with respect to I minus 1, not only rotation, but even its position. Only matrix will be used directly to define your ith frame with respect to I minus 1th frame. How to write it? How to get those? Yes. So here is the extended view of what we have shown for the multi-body systems. And say this is my link connecting to this. I minus 1th link, this is I minus 1th joint, and this is I joint. Now I told you what is the meaning of all these joints. Joints are coming from, again, 1 to n, and the links are also 1 to n. So you will see that these are the joints. Hello, okay. So the first thing is, first, there are only 3 steps. First is affix frames. First important thing is, it's not that you fix the frame in any direction and then the DH parameters will work. No, this will work only when you have fixed the frames according to DH conventions. How it fixed? Very easy. I want to change the color. Very easy. First, I will take the Z's, the X's. Take all the X's, like not only for I minus 1 and I mean 0, 1, 2, 3, for any axis. Just draw the large lines, okay. Then take there, between the two axes, say this is my Z I minus 1 and this is Z I. Just draw all the axes, and then out of those all axes, you take this particular common perpendicular. And you know what? These common perpendiculars, if I just go back, okay, I'll just go back in 1 minute only. And this common perpendicular in the skew lines will be visible, but in intersecting, the common perpendicular, of course, it has value 0. It will be the intersecting point only. In parallel lines, for example, there are parallel lines that Z0 and Z1 are say parallel. Then there are many places you can have common perpendicular, right? So you can take any point. And if the Z1 and Z2 are intersecting, then this is the common perpendicular, perpendicular to this. So this common perpendicular is to be taken. Now, how to affix the frames? The frames are very straightforward. What you do is, where the common perpendicular of I minus 1 and I joins or intersects the ZIF minus 1, that is the first Z, that is our origin for I minus 1. The direction towards the common perpendicular is your X I minus 1, and this is your frame ready. Similarly, they may have some common perpendicular from Zi to Zi plus 1, somewhere else. I'm just taking this as, maybe it is OI here, and then this will be the direction of your XI, and ZI anyway is this. So you do not need whole line later. In the beginning, you just make all the lines. I do this exercise back at one quickly. Anyone, wherever I'll see a clean location. Okay, this. So here, if I have to do, as I said, first step is to affix the frames. First step is just to take long lines in the Z's, in the Z directions. Okay, this is in the X's. This is my X's, this is my X's, this is my X's, long lines. Second is common perpendicular. So I'll take a Z reference frame. I'll say this is my RR. Okay, so this is my first is Z1, this is Z2, and this is Z3, and Z0 is also I'm taking in the same direction of Z1, right? This is straight. Okay, so where will be my frame? The frame is from Z1 to Z2. This is my Z1, this is Z2. So of course the two are intersecting. So this is the common perpendicular. So X can be any direction. X1. Now Z2 and this is Z3. The two are parallel. So I can take. So this is my Z1. This is the first frame. Z1, X1. Y1 is of course from right hand rule. And then the Z2 and Z3 are parallel. You can take actually the frame anywhere, right? But you would like that, okay, where this is matching Z2. So you can always have, if this is the one, this is the second, and the perpendicular is there, you can take anywhere on it, right? Anywhere on it. So you may like to take exactly at the joint. So that gives you third, and the third is with the virtual, say Z4 is virtually there. You can take, of course, anywhere. So you may like to take, this is your Z3 and this is your X. So my point is, once you know the method and the convention, it becomes just a procedure. And idea is not to know the procedure. Idea is to know why we are using the procedure, right? So you will affix the frames. Once you know the frames, then it's very straightforward to write the 4 parameters, which is the last point for today. The first parameter is your twist angle, which is denoted as alpha. And the twist is the twist between Zi minus 1 and Zi, okay, about, this is an angle about Xi minus 1, right? So going from Zi minus 1 to Zi, very straightforward, you can write it. So that means if I take the two parallel, this is Zi minus 1, and if I take Zi's parallel link here, this is the angle from Zi minus 1 to Zi about Xi minus 1. This is my alpha I minus 1. Okay, you know what it has done is, if you rotate about X, and then Zi minus 1 will become Zi. They will become parallel. Right. Okay, what is the second? The second is actually our, this twist angle is your first parameter. Second is your this distance, and that is your link length, we call it. And link length will be A as normally being denoted. It is along Xi minus 1. That means this distance. So that means the distance of the common perpendicular is your AI minus 1. Index is important, going from Zi minus 1 to Zi. So these, see, in one lecture, you may not quickly be able to do yourself, but it is so easy that once you do exercises of 2 or 3 in your book, or if you are like studying it, it will be very straightforward. Then the third is, you know what has happened is, from here after rotation and after this A, your frame has moved from this place. First it has rotated, and then it has come here. So if you'll take these two steps, like about Xi minus 1, if rotation alpha, and along Xi minus 1, the distance A is covered, so the frame is already here. Now we want this frame to come here. And the moment we do these 4 steps, you will get the transformation matrix using the 4 steps. So now next is our distance between two X. So now, you know, this is Xi minus 1, not this, I mean this, right? So basically, third is your offset. Offset is, yeah, I'm quickly closing in 2 minutes. So offset is your DI, and that is along ZI from Xi minus 1 to Xi. And finally, you have your joint angle, which is theta I, which is after, you know, it has reached here about Zi. If you rotate, for example, this is this particular frame which has reached here. So the two will be aligned if you rotate about Z. So about Z, I from xi minus 1 to xi. So it's a very defined exercise which helps us that what are these four parameters. And the moment you get your alpha I minus 1, ai minus 1, di, theta I for any I. So now you can very well write for those 3 degrees of freedom or 6 degrees of freedom. From 0 to 1, what we were writing is actually if I is 1, depends upon how many degrees. Say if we have only 3 degrees of freedom, then you'll write, okay, the first will be your alpha naught. See, alpha naught. So alpha naught will be the angle between Z naught to Z1 about X naught. So this is what I'm just using the previous exercise, this definition. And if you apply it on your mechanism, you will be able to write this particular parameter. And after that, from each parameter, you get a transformation matrix from T1 to T0. From second, four parameters, you'll get T2 to T1. Third, you get T3 to T4, and fourth is this. And in totality, if you know homogeneous transformations, even if you don't know, I mean, you need to study it. I just showed you that how the rotation will be represented for for rotation matrix helps us both as orientation as well as for its for as an operator. Similarly, transformation matrix gives both orientation and its frame and its position. So if you now take 4 with 3, pre-multiply them, this one with 0, okay, why I missed 3 with 2, right? So if you pre-multiply these four, you will get the frame 4 with respect to 0. And how these transformation matrices will be written, that is very straightforward. Once you know a set a I minus 1, alpha, d, and theta I, there is a fixed matrix in the book, which I'm not writing because now this is the book stuff. And you have cos theta I, sin theta I minus, right? And you have 0 and a alpha I minus 1. And then here also you have di. This is minus of sin alpha I minus 1, and this is plus of sign. Similarly, you have other terms. So I just remember a few quick terms. And for example, here is theta I cos alpha I minus 1. Similarly, you have other very fixed terms. So if you know this, for any four parameters, you will be able to write, say, I know my four parameters for t1 to 0, right? Normally in T1 to 0, say alphas are 0. If alpha is 0, this part will be 0, this part will be 0, A is 0. All these will become 0, and totally you will get cos theta cos 1 minus sin 1, 0, 0, sin 1 cos 1, 0, 0. And in fact, you will get exactly this matrix. It's very straightforward. In totality, you get your model. So I would like to complete by just showing you finally this particular, just introducing that you can actually practice. I always say that I try to uplift the Indian versions, and this particular robotic Robo Analyzer is actually the software developed by IIT Delhi by Professor Saha. And normally, if he gives a presentation, I think he'll give the entire on it. But sometimes I feel that fundamentals first you know, then you use it is better. See how you are changing the joints, and at the back, the same equation which I have showed you is being used by their students, and the software is being ready. So you can always see that the lengths and the breadths, everything, and just by changing the theta 1, theta 2, 3, or 4, you'll be able to see the entire workforce. So this is all I wanted to show. And this workspace is again developed using the same models like in MATLAB. You can practice. And finally, I would like to thank you for the listening, because this is just to introduce to you punch robotics, which she mentioned in the beginning. I have started with this. And so I would like to say that kinematics takes more time, but this is all about the relation between last and the front. That is the end effector and the first point. So if you know the frames of fixation, you know everything. So with this, I would like to close and thank you very much for your patience. I would like to just add on, stop sharing. All right.
Thank you so much, ma'am. Yes, dear all, please ask your queries. If you have any, you can post your queries in chat box also. Thank you so much, ma'am, for your kind presence. You explained it in very graceful manner, and it was very interesting session. Let me check if there is any queries.
There are two chat points. Okay, attendance. Okay.
Okay, so there is no queries at all, ma'am. Thank you so much.
Thank you.
Yeah,
Okay,
it
I'm
was.
sure that because we have to do some kind of, we are not never sure of the audience. Sometimes audience could be some people who know it far behind, and for them it is kind of the alphabets and they already know it. But point is, if you are such and you would like to have any issue with your research, you may please write us and we can help you. But because it was told that it is basically for the fundamentals first, and I don't know where the audience is for, and so I always want to connect it, so that they should not feel it is difficult and to start with the basic terms. So thank you very much, and
Thank you so much, ma'am.
I'll get a call from director. There's a head meeting at 3:30. Thank you.
Thank you, ma'am. Thank you.
Thank you very much. I have to go. Thank you very much.